Advanced Engineering Physics, Unit 2, Quantum Mechanics. Fundamentals of Quantum Mechanics. Quantum mechanics is the branch of physics that describes the behavior of matter and radiation at atomic and subatomic scales. Classical mechanics successfully explains the motion of macroscopic objects, such as planets, vehicles, and projectiles, but it fails to explain many microscopic phenomena, such as atomic spectra, black body radiation, and the stability of atoms. Quantum mechanics was developed to overcome these limitations and provides a completely new picture of nature in which particles exhibit both particle-like and wave-like properties. Physical quantities are often quantized, and measurements can only be predicted probabilistically rather than with absolute certainty. One of the most revolutionary ideas in quantum mechanics was proposed by de Broglie. He suggested that every moving particle possesses an associated wave nature. According to the de Broglie hypothesis, matter and radiation are not fundamentally different. Both exhibit wave-particle duality. The wavelength associated with a particle is called the de Broglie wavelength and is related to its momentum by the equation P equals h divided by lambda, where P is the momentum of the particle, h is Planck's constant, and lambda is the wavelength associated with the particle. This relation shows that particles with large momentum have very small wavelengths, which is why wave properties of everyday objects are not observable, whereas electrons, protons, and other microscopic particles exhibit clear wave behavior. The de Broglie hypothesis was later confirmed experimentally through electron diffraction experiments and became one of the cornerstones of quantum mechanics. This wave nature also explains why a particle confined within a small region cannot possess arbitrary energy. If an atom or electron is trapped between fixed boundaries, only specific wavelengths can exist inside that region, and these wavelengths determine the allowed momenta and energies of the particle through the relation kinetic energy equals p squared divided by 2m. Another fundamental principle of quantum mechanics is the Heisenberg uncertainty principle. This principle states that certain pairs of physical quantities cannot be measured simultaneously with unlimited precision. The most common form of the principle relates position and momentum, and states that the product of the uncertainties in position and momentum is always greater than or equal to cross divided by 2. In simple terms, if we try to determine the exact position of a particle, our knowledge of its momentum becomes uncertain, and vice versa. Similarly, energy and time are also connected through an uncertainty relation. This energy-time uncertainty has important consequences in many physical systems. For example, if a quantum state exists only for a very short time, its energy cannot have a single exact value, but instead spreads over a range of energies, producing what is called lifetime broadening. Thus, uncertainty is not due to imperfections in measurement instruments. Rather, it is an intrinsic property of nature itself and sets the ultimate limit on how precisely physical quantities can be known. The state of a quantum particle is completely described by a mathematical function called the wave function, usually represented by psi. The wave function itself does not represent a directly measurable quantity. Instead, its physical significance lies in determining the probability of finding the particle at a particular location. According to the probabilistic interpretation proposed by Max Born, the quantity psi star multiplied by psi, or the absolute square of the wave function, gives the probability density of the particle. This means that the probability of finding the particle in a small region of space is proportional to the square of the magnitude of the wave function in that region. If the wave function is large at a certain point, the particle is more likely to be found there. If the wave function is 0, the probability of finding the particle is 0. For a free particle represented by a traveling wave of the form exponential of ikx, the probability density remains constant throughout space, indicating that the particle is equally likely to be found anywhere. However, for standing waves formed due to interference or confinement, the probability density varies from place to place, resulting in regions of high and low probability. This spatial variation in electron probability is one of the fundamental reasons behind the formation of energy bands and band gaps in solids. Quantum mechanics describes measurable physical quantities using mathematical entities called operators. In classical mechanics, quantities such as position, momentum, and energy are represented simply by numbers. In quantum mechanics, these quantities are represented by operators that act on the wave function. For example, the momentum operator in one dimension is given by minus IH cross d by dx, while in 3 dimensions it becomes minus IH cross times the gradient operator. Similarly, the total energy of a system is represented by the Hamiltonian operator. For a free particle moving in one dimension, the Hamiltonian operator is equal to minus h cross square divided by 2m multiplied by the second derivative with respect to x. When the Hamiltonian operator acts on the wave function, it produces the famous Schrödinger equation, which is the fundamental equation of quantum mechanics. Solving this equation allows us to determine the allowed energies and wave functions of a quantum system. An important concept associated with operators is that of eigenvalues and eigenfunctions. When an operator acts on a special wave function and reproduces the same wave function multiplied by a constant, the wave function is called an eigenfunction, and the constant is called the corresponding eigenvalue. Mathematically, this is expressed as operator acting on psi equals lambda psi, where pi is the eigenfunction and lambda is the eigenvalue. In the Schrödinger equation, the Hamiltonian operator acting on the wave function psi n produces epsilon n times pi n. Here, psi n represents the eigenfunction or quantum state, while epsilon n represents the allowed energy level of the system. Thus, quantum systems do not possess arbitrary energies. They can exist only in specific energy states determined by the eigenvalues of the Hamiltonian operator. This quantization of energy is one of the most important features distinguishing quantum mechanics from classical physics. Finally, because quantum mechanics is fundamentally probabilistic, the result of a single measurement cannot always be predicted exactly. Instead, we calculate the expectation value of a physical quantity, which represents the average result obtained after performing a large number of identical measurements on similarly prepared systems. The expectation value is therefore the most probable average outcome of an experiment. For example, the expectation value of momentum is obtained by integrating the wave function, the momentum operator, and the complex conjugate of the wave function over all space. Expectation values play a central role in quantum mechanics because they connect the abstract mathematical formalism of wave functions and operators with experimentally measurable quantities. In summary, quantum mechanics introduces a completely new description of nature. According to the de-Broglie hypothesis, particles exhibit wave-like behavior. The Heisenberg uncertainty principle establishes fundamental limits on measurement accuracy. The wave function provides a probabilistic description of a particle's state, while operators represent physical observables such as momentum and energy. The allowed values of these observables are obtained as eigenvalues of the corresponding operators, and expectation values provide the average measurable outcomes. Together, these ideas form the foundation of modern quantum mechanics and provide the basis for understanding atoms, molecules, solids, semiconductors, lasers, and many of the technologies that shape the modern world.